Okay, last lesson is nothing new. It's more of just the application of the stuff we did in the last 2 lessons, which is great. Okay, this is a unit that we can really get our hands around. There's no one-off lessons except for maybe the mean value theorem, which is something that we did after the first lesson and we haven't looked at, since. But you'll have to remember that for the test. But today we're just kind of throwing things all together, tying it all together. I have 4 pieces of graph. I asked you to identify the signs of f prime and f double prime, given that these are all pieces of f, of course. Well, if you know if something from left to right is decreasing, we know that f prime is negative. If I know something is concave up, I know that f double prime is positive. And I can keep going down the line. Now we are increasing. That means our first derivative is positive. And we're concave up still. Second derivative remains positive. And I can keep going. This, and if you can kind of combine this, you can see how this looks like x squared. So in the graph of x squared, we have a piece that is decreasing concave up and a piece that is increasing concave up. Here, this would be like the graph of negative x squared. We'd have a piece that is increasing concave down. So f prime is positive, but f double prime would be negative because we're concave down. And then this piece would be decreasing concave down. All right. Well, kind of understanding this, creating this, we can kind of combine information about f and f prime to sketch a really good, decent approximation of what f is going to look like. Now, where things are going to be located, we're not sure of that. It can be located anywhere, but at least we'll know what it'll look like. So here I give you some information about f prime and f double prime. You can copy that down. And then what we're going to do is sketch f given that information. And then I want you to identify maxes and mins and inflection points of f. Well, we can identify where our maxes and our mins are and where our inflection points are right away. But what's going to really help us out is if we can understand what the pieces of our graph will look like on all these intervals. So I have f prime, I have f double prime. This will enable me to sketch f. And I'll go ahead and kind of put all of these interesting points that I have for f prime and f double prime down here. And I can really look at my first derivative to see that I'll have a min of f at -2. I'll have a little max, a relative max of f at 0. I'll have a min at 2. And then I'll know that looking at f double prime, these will all be inflection points. So I know that. Now I just need to know what the pieces of f will look like. Well, using kind of this information from above, I know that when f prime is negative and when f double prime is positive, we are decreasing concave up. F is going to look like that, to the left of -2. For the next piece between -2 and -1, I'll be positive for f prime and positive for f double prime, I'll be increasing concave up. It's going to look like that. You guys fill in the rest of the pieces. Kind of tricky, right? It's tough to see it in your brain sometimes. Just go back to this original thing. Go back to being concave up, which is this, or being concave down, which is that. We are increasing, we are decreasing. Here, we are decreasing and increasing. So let's see if you got at least the ones that I got for the couple that you did. Between -1 and 0, I'm going to be increasing concave down. That's like that. Then from 0 to 1, I'm decreasing concave down. That's like that. Then decreasing concave up. There's that. Increasing concave up. Put it all together, and this is what the graph of f could look like. -1, -2, 1, and 2. I'll be decreasing concave up, increasing concave up till we hit an inflection point, increasing concave down till I hit a max, decreasing concave down, another inflection point, increasing concave or decreasing concave up till I hit a min, increasing concave up. Neat. This is an accurate graph of f. Now, of course, I can move f to look anywhere, and I'm not exactly sure where these mins or these maxes are. But if I were given more information, maybe I'd get an even more accurate graph. Okay? So that's it. Well, I could kind of give you the graph of f prime and ask you to graph an accurate or a visually accurate graph of f. What you would need to do is create those two number lines that were given to you in the previous problem. You need to create f prime, and the signs of f prime you'd have to analyze. And then you have to analyze the signs of f double prime so that you can then look at what the graph of f will look like on these specific intervals. So f prime, we look at the values, negative below the x-axis, positive above. We are negative until we get to -2. We are then positive until we get to 0, negative until we get to 2, positive thereafter. F double prime, we would create something as well. We would be looking at the slopes of the tangents of f prime to get the values of f double prime. They'd be positive to the left of -1. They'd be negative until we get to 1. And then they'd be positive thereafter. And if I am not mistaken, it's the exact same graph as this. Okay? So we don't even have to sketch it. But you can at least see how you can produce that and that, and then you could go ahead and say, okay, and this actually cuts out some time, we would have pieces of f that would look like this. And we'd find out exactly where our inflection points are, and we'd go from there. Okay? Cool. Now I can give you a function and ask you certain questions about the function. Not necessarily where just the relative extrema are, not where the inflection points are. I could say, given f of x is equal to x cubed minus 3x squared plus 3, find when this function is both decreasing and concave up. Well, decreasing is when f prime is negative. Concave up is when f double prime is positive. We just kind of do what we've been doing. We just do it at the same time. We'll do that first derivative test to test for increasing and decreasing and extrema. We'll then do that second derivative test to figure out where we're concave up and concave down and where we have possible inflection points. And then we throw them on top of each other and see when we have a negative first derivative and a positive second derivative. So let's do it. Take the first derivative. I'll set that equal to 0. I get 0 and 2. So over here, I will look at f prime around 0 and 2. Positive values, we'd have negative values, we'd have positive values, so that helps me determine where we're increasing and decreasing. Then I would go ahead and do the same thing for my second derivative. I get 6x minus 6. Set that equal to 0. I get x is equal to 1. And right underneath f prime, I'd produce a graph of f double prime. And I'd evaluate the signs of f double prime around 1. Greater than 1, we'd be positive. Less than 1, we'd be negative. Decreasing, concave up between 1 and 2. It's that simple. If I wanted to sketch what this would look like, you could. It'd be increasing concave down, decreasing concave down, decreasing concave up, increasing concave up. Kind of throw these pieces together, and you would have the graph. Something like that. Which makes sense if it being a cubic. Okay, intro to speed. Start off with a tricky problem. There's f of x. F of x is equal to 1/3 x cubed minus 2x squared minus 5x. I ask, when is f prime increasing? And this is key to understanding how to do this problem. Anybody know what I should do? Anybody have an idea? Ah, that's it. Okay. Here's the thought process. F is increasing when what? When f prime is positive. Good. Well, let's go down a step. F prime is increasing when what? F double prime is positive. You can just go ahead and just say something is increasing when the derivative of that something is positive. If you want to see when f prime is increasing, you will look at when f double prime is positive. If I'm wanting to look at when velocity is increasing, I'll look at when, well, that's another whole, usually you don't say when velocity is increasing. We'll talk about speed, so let's not do that. Anyways, when like a population or a change in a population is increasing, you look at the derivative of the change of the population and see when that's positive, you know? So for this guy, I would have to take the first derivative. I'm sorry that I'm doing this quickly, but we got to move on. And then go ahead and take the second derivative to figure out that around 2 we'll see a possible change in my second derivative. Bigger than 2 or positive, less than 2 or negative. When is f prime increasing? When x is greater than 2, or from 2 to infinity. Okay? But make sure we get this down. And this, and this, and this. Because that is crucial. Because you'll see it on an AP exam. And on your quiz. And that's kind of the introduction to speed. Speed is velocity without direction. Or it's the absolute value of velocity. Always positive. So something could have a positive or a negative velocity. Okay? My question is, when is something speeding up? Or when is the speed of something increasing? You would think that, right? If I have a positive acceleration, I must be speeding up. Well, have we seen this guy before? Good. I love this guy. This guy's great. Well, here I have a positive acceleration, but he has a negative velocity. Is he speeding up or slowing down? So let's try it again. Negative velocity, positive acceleration. He is, oh, he hit the wall. Let's start again. If he starts here, let's give him a negative velocity, a positive acceleration. Let's see if he's speeding up or slowing down. Slowing down. Now notice, now he's speeding up. And we're talking about speed. So speed is just, is something speeding up? Is it going faster? This guy is speeding up. Now he's slowing down. Now he's speeding up. Now he's slowing down. Speeding up, slowing down. Speeding up, slowing down. Look at velocity and acceleration and tell me when something is speeding up. Mr. Glubke, what'd you say? Exactly. When acceleration and velocity have the same signs, we are speeding up. We could be speeding up in the positive direction, or we could be speeding up in the negative direction, and that's the key. When is something speeding up? When the velocity and acceleration have the same signs. When is something slowing down? When velocity and acceleration have opposite signs. If I'm going in the positive direction to the right, but my acceleration's to the left, I'm slowing down. I'm trying to eventually go back to the left. If I'm going to the left, but my acceleration's to the right, I'll be slowing down until my velocity turns to be positive and I start having velocity and acceleration going the same way. So here is a question. The position of a particle is given by this function, negative t cubed minus 3t squared. The question is, when is the speed of the particle increasing? Well, we got to figure out when V and A have the same sign. How do I do that? I just go through the process of finding the derivative, its critical points, if it's positive or negative, to the left and right of those critical points. Then I do it with the second derivative to find A, find the critical points, find when it's positive or negative, and we just go from there. So first we find V by taking the derivative of x. I get negative 3t squared minus 6t. Set that equal to 0. I get t plus 2, giving me 0 and negative 2. Well, this gives me the signs of V. I look to the right of 0. I got a positive times what would be a negative, actually. So this is a negative. I look between 0 and negative 2. That's a negative times a positive. That's also, wait, what? Is that also a negative? Positive times a negative. This is, yeah, this is a positive times a positive. Thank you. And then this is a positive times a negative. This is a negative. Okay, so that's the start. Now we do the same thing with my acceleration function, which is just the derivative of velocity. So that's negative 6t minus 6. I figure out t is equal to negative 1 when we set this equal to 0. Plot down a of t, negative 1. We look at values bigger, like 0. I get negative 6 if I plug in 0. If I plug in values that are negative, I'll get positives. So when is my speed of this particle increasing? Between negative 2 and negative 1, and between 0 and infinity. This is when V is positive and A is positive, but also between 0 and infinity, we will have a velocity that is negative and an acceleration that is negative. Okay?
You just put parentheses around that
yes,
interval?
around that interval, but you know, 2 different intervals.
Okay, well, I've been doing brackets. I just
Oh yeah, parentheses because we are stopped at this point of negative 2, right? If my velocity is 0, we are stopped. Now this is also important. What is something moving to the left? This is important to write down in your notes. When is something moving to the left? We have 3 minutes still, so let's make sure we have. Velocity is negative. Very good. Moving to the left if velocity is negative. So if you're asked a question in your homework I need to give to you, I will. It's a handout and there's book problems. Yep, but you're going to do the book problems on the back of your homework, so it's not that bad. They're mostly just graphs. So you're moving to the right when your velocity is positive. That's important. When are you stopped? On the velocity 0. Good. Make sure we understand that. Okay. I could give you, what? Go back. What? I could give you the graph of velocity. And ask you, when is the speed of the particle increasing? Go figure that out while I hand out your homework. That's the velocity of a particle. I'm asking you, when is the speed of that particle increasing? Draw a number line if you need to. On the front of your homework, once you get it, write down "do book problems" on the back. That way you just hand in one big packet. All right, don't leave until I get through this. We need to examine velocity and acceleration to see when the speed is increasing, which is when the signs are the same. Velocity is positive here, there's negative here. We're starting at 0, but we have nothing to the left of 0. Velocity is positive until 2. It's negative until 4. Positive after 4. The acceleration would be the derivatives of velocity, or the slopes of my velocity function. They are positive until 1, negative until 3, and then positive thereafter, which means I am speeding up between 0 and 1, between 2 and 3, and then after 4. Yes?
Can you also just look at where it's moving away?
That's when the signs would be the same. I like it. All right, thank you. That's pretty much it for the notes. I might have one extra problem. Yeah, one extra problem I'm going to do on the video, but that's it. Well, let's talk about slowing down too. I didn't really touch on slowing down. We are slowing down, or this is the same as speed decreasing. So speed is decreasing when the velocity and acceleration have different signs. That's between 1 and 2. Because velocity is positive while acceleration is negative, and then between 3 and 4. Velocity is negative, acceleration is positive. Okay, last question. The velocity of a particle is given by this function. The question is the particle speeding up or slowing down when t is equal to 2/3? Well, all I need to know is the signs of velocity and acceleration. At 2/3. Well, to find the sign of velocity at 2/3, I just plug in 2/3 into my velocity function. It becomes the sine of 2 pi over 3. And the sine of 2 pi over 3 is positive. I don't even care what it is. I just know it's positive. It's in the second quadrant. Sine is positive in the second quadrant. So we're good. Now let's look at our acceleration. To find my acceleration, of course, I have to take the derivative of velocity. So that's cosine pi t times pi. I then figure out what the acceleration is at 2/3. That's cosine of 2 pi over 3 times pi. Cosine is negative at 2 pi over 3 times pi. That would be negative. That means my particle is slowing down because the signs of velocity and acceleration are opposites. All right, that's it. I like it.